I share screen with all of you. We are at this chemical bonding, right? Okay. All right, here. Can you all see the screen? Okay, here is the electrical conductivity. I think we stop here. Okay, let me finish all the notes first, then we go into the tutorial. Okay, so I think that is cleaner. Okay, so I just give you all the overview 8.8, the electrical conductivity. Okay, so you learn that in O level that this simple molecular substances are usually non-conductor electricity because they don't have ions and electrons. Okay, so that is generally true, except for the 0.2 over here. If they can ionize in water, this is a point that you all need to take note. Okay, so this is one of the very I wouldn't say it's a misconception, but maybe it's a bring over from O level. A lot of students keep telling me HCl is ionic because they see HCl dissociate in water. Okay, because of this reaction. Remember, I think I told you all before. I think when I ask the dot and cross diagram for O level student, they always draw for me the HCl as ionic, which is wrong. Also, you must understand, even though it ionizes in water, it is still a covalent compound. So if you draw a dot and cross diagram, it should be a dot and cross diagram of a covalent compound, not ionic. Okay, similarly for ammonia, I think you all know what I'm talking about, right? Ammonia, same thing, inside water give NH 4 plus and then OH minus. Okay, I understand why people keep thinking they are ionic because of these two reactions. Okay, but again, you must understand the context. This is a reaction, so-called a reaction in water. The ionizers in water, naturally without water, they don't go through this kind of reaction to form ions. Okay, so when you are asked in for dot and cross diagram, I mean, of course, that happened at O level. Okay, so at O level, when they ask for dot and cross diagram, always go back to fundamental. Okay, these are non-metallic. Hydrogen, chlorine, nitrogen, hydrogen, all of them are non-metallic, right? So in the first place, they will actually undergo ionization only in water, then they form ions, then they can conduct electricity. Also, there's the only exception to the rule, so you all can put a double star there. Okay, okay, let's go on to giant covalent compound. Okay, I think you touch on it in pure chemistry syllabus for O level. We can go straight into describing the lattice structure. Okay, so this one is a giant molecular structure, extensive network of covalent bond, carbon-carbon bond. Okay, there are two of them very famous inside your syllabus, diamond as well as silicon dioxide. Okay, so the other one you need to remember SiO2. Okay, of course at A level they can give you other example like boron nitride. Okay, boron nitride is another one. So I just write down here. You all can jot down. Very famous one. Your teacher will always use as example inside your exam or inside tests. Okay, the boron, especially compounds with boron, okay, very similar to diamond. Okay, so these are very strong. Okay, they are giant molecular structure. Giant covalent molecule at O level, we call it GCM, right? Giant molecular structure, GMS. Okay, so now the correct term we use is macromolecules. Macro means huge, micro means small. So that's why the term used is macromolecule. Okay, so some of this example you can see below, silicon dioxide, graphite, and diamond. Okay, so let's go through diamond. Okay, so I think you all know why the bond angle is 109.5 here. Tetrahedral, right? Remember we went through the mother structure is tetrahedral, the actual structure is also tetrahedral. Okay, so it extends all the way through in this kind of three-dimensional arrangement of carbon atoms. Okay, so all of them are sp3 hybridized. Okay, so remember hybridization, they are all bonded to 4 other carbon. So this is repeated throughout this entire structure, interlocking. Okay, so that's why you know why people pay more for diamond ring. That's one reason. Okay, right? Obviously, diamond and graphite, they are known as allotropes. You all know this term of allotropes. Okay, because they are both allotropes because they are both different forms of the same element, carbon over here. Okay, so over here you can see that's why diamond is the natural hardest and natural occurring substance over here. Okay, so you can see why they say that this thing is a woman's best friend, because supposedly the real love should be as hard as diamond. Okay, but that is what people always feel. That's why diamond ring is asked to use as an engagement ring or even as a wedding ring. Okay, so that is a reason. Nobody go for graphite ring. Okay, even though it's the same carbon. Okay, right. So you laugh. Next time you try, you propose to your girlfriend with a graphite ring. Okay, see whether it can work or not. It didn't work for me. So I still have to spend a lot of money to buy the diamond ring. Okay, right. Okay, point 3, they does not conduct electricity because they don't have delocalized electron. Now remember, that's the difference between diamond and graphite. Okay, diamond cannot conduct electricity, but graphite can. Because remember, graphite, 3 electrons are being used. Later, I'll show you the structure for graphite. Okay, so diamond is very high melting point because of strong covalent bond. Okay, remember, whenever we talk about the giant molecular structure, right, we don't talk about the van der Waals forces. Okay, I notice sometimes candidates like to talk about van der Waals forces between the graphite layers. Graphite layers got van der Waals forces. You are right. Okay, but you think about it, just like what I told you, right? Whenever we talk about melting point, we are trying to break the strongest bond possible. Last week, we talked about hydrogen bond, PD-PD, and ID-ID. Whenever there's hydrogen bond, right, we don't talk about PD-PD and ID-ID. Or we leave them aside. Okay, no point you give the examiner one whole para of everything about your dipole moments, got ID, then got hydrogen bond. That's why more energy is needed to overcome that. Don't need. Okay, just straight to the point for the strongest bond possible. Okay, so 0.4, 0.5, they are 0.5, the diamond is unable to dissolve in water. Okay, in fact, it's so hard that if you throw inside the microwave accidentally when you bake a cake, when your cake is out, right, your diamond ring should not melt. Okay, if your diamond ring melt, you can be sure that the diamond is fake. Okay, so this is some test that Rachel, you can do yourself next time. Okay, when you receive your diamond ring. Okay, so you can confirm whether the diamond is real or the love is fake. Okay, either one. Okay, right. So sometimes some people like to buy a fake diamond ring for the wife or the girlfriend. So you just place it in the microwave, switch to the maximum, and then when you open up, the cake is big. And the diamond also big, melted, confirm is fake. Okay, so use chemistry to your knowledge. Next time your friends ask you how to test whether diamond is real or fake, that's the best way. Okay, if you cannot withstand the the oven temperature is how much? Cannot, not very high, right? It still melt. That means your diamond is questionable. Don't know buy from where. Okay, Little India or what? Okay, no, just a joke. Okay, pasar malam. Okay, so this is how you test for the how whether you know a diamond is real or not. Okay, can okay, so silicon has the same structure as diamond, but however the bond between silicon are weaker compared to the diamond itself. The melting point of this silicon is lower at 1410 degrees Celsius. Okay, so you know now why? Do you all know why? This point here. I know we always give this in lecture, but no student really asks. You know why or not? Because you look at periodic table, silicon is below carbon. Atomic mass of silicon larger. Correct or not? Larger. Remember what I told you about overlap. The best thing is 10 cent coin overlap. Then as you go down the group, what happened? The bond length increases. Why? Because the atomic size increases, right? So your overlap become less efficient. Okay, so as your bond length increases because of the size of the atomic radius increases, silicon is bigger than carbon. So the silicon bond strength, bond length is longer than carbon bond length. That's why you need lesser energy to break the silicon bond. So you can jot down somewhere. So always relate, use knowledge across all the topic to help you understand atomic radius, link to bond strength, and then explain why silicon is weaker. Okay, so stand by for this if you are asked. Also explain your own words based on your knowledge of atomic radius, and then how the bond length increases lead to a decrease in bond energy. Because this is covalent bond, we are not breaking van der Waals forces. Correct? So don't get confused. Remember I told you before, right? When MR increases, van der Waals forces increases, in extensiveness increase, your boiling point, melting point increase. That is correct. But that is intermolecular forces. Over here for silicon and diamond, we are talking about intramolecular forces, intramolecular bond. Intramolecular bond got to do with the size of the atomic radius now. So when you explain, please explain using the correct terms. All right. So this is silicon dioxide. Can you see sand, common sand that you see at East Coast Park? Also, same thing. You can see silicon over here is bonded to 4 oxygen atoms. Each silicon oxygen atom is bonded to 2 silicon. Can you see the bonding? Okay, this is a oxygen atom, and then your silicon over here. Okay, SiO2. So this is your Si, and then in between here is oxygen. Okay, is it clear now? Okay, so the black dot over here, SiO2, this black dot is just to show you there's 3-dimensional coming out. Okay, so this is silicon. So maybe you all can highlight. Can you see this one in the center? Okay, I change to my pen. The red one, this one, the red ball. This is this one. Okay, then your oxygen atom, I change to this color, okay, green color, shade, this one. Okay, sorry, this one, this one, this one, and the one behind. Okay, right. Ignore all the black balls. The black balls is a 3-dimensional to show you that another layer is on top. Okay, so that one, just ignore it. Okay, so just, I don't know whether y'all can see this, this green ball is hidden by this black ball. Just below there, got one more green ball. So that is your oxygen atom. Okay, this oxygen atom here. Okay. Your one you can Google online. There are also diagram online. You can see very clearly how silicon dioxide look like. Oh, same thing. So this is how your quartz, there is an oxygen atom between 2 silicon atoms. Arrangement is very similar to diamond. Okay, exactly the same tetrahedral shape. Okay, so now this is the meaning of silicon. Just like I mentioned, why the silicon bonding is weaker. So the bond length is longer between the 2 carbon atoms. So there's an info which I actually highlighted. Larger means actually this word larger is talking about atomic radius. If you want to go down to the atomic atom level, at the atom level, so this makes sense because as you go down the group, you're adding additional quantum shell of electrons. So that is why silicon is weaker compared to diamond. So you must stand by. This question over here you might be asked. Then after that, they can also ask you to predict. Let's say they give you another element even lower than silicon. When they ask you if there's a giant molecular structure formed from this element, predict the melting point, explain. Okay, something along that line. Okay, so that is actually testing you on the atomic radii pattern. Okay, the trend as you go down the group. Okay, next one, 9.3 is graphite. Graphite has a layered structure made up of many planes of interconnected hexagon shape of carbon. Okay, so you see this one, or we describe it as a beehive. If you look at this beehive, right? You all know beehive, always draw like that one, right? Hexagon shape. This is hexagon, can you see? So every carbon, can you see this black dot which I circled here? Every carbon is only bonded to 3 other carbon. There's 1 more electron left per carbon. That is why graphite can conduct electricity across the layer. Okay, can you see across the layer? Okay, you have electrons which are free to move. Okay, between them is van der Waals forces. All right. So this one is sp2 hybridized now. Remember sp2 hybridized. Where did we see it before? Alkene. So very similar to alkene, except there's no double bond. Okay, can you see there's 1 more loose electron here? Loose electron here. By right, you should have a pp overlap to form double bond for alkene. Okay, so that's why it's sp2 hybridized. sp2 hybridized means you have 3 orbitals involved in bonding. 3 hybrid orbital. 3 of them. So very similar to that of your alkene. You form 3 sigma bond, therefore it's the trigonal planar. Bond angle is 120. Okay, so we have seen that last week for trigonal planar shape in the sense is sp2 hybridized, because remember in your VSCPR theory, double bond is considered as single bond, or triple bond, double bond, or is considered as single bond. Okay, so now it has a unhybridized p orbital. That's what single electron, you can actually sideways overlap. So that's why it form a cloud, a pi cloud above and below the carbon atom. Okay, so I will draw on this diagram. So what they are trying to say is that actually you can see for each of them over here, there is a p orbital, and this one got one p orbital, p orbital. Can you imagine? All of them got p orbital. So they will do a sideway overlap, so-called the sideway overlap with each other to form this pi electron cloud, but there's no double bond. So the electrons are free to move. That's why we use this term delocalize. Okay, delocalization of your electron, and therefore it's an electrical conductor. Okay, right. So you see, some student will ask me how I know it's parallel to the layer and whether it's perpendicular to the layer. Can you see? You can conduct electricity parallel or perpendicular to the layer. Okay, so doesn't mean that it will sometimes conduct electricity, sometimes don't. Okay, but remember in the context of the whole graphite, right? Let's say your pencil, you cannot tell whether, you cannot see with your naked eyes whether it's parallel or perpendicular. So don't try your luck. Okay, some students say, oh, that means if it's perpendicular, then it don't conduct electricity. I can actually place it in the electrical socket. Then you still get electrocuted. Okay, so never attempt doing that. That is very dangerous. Okay, so graphite is so this term here is not to worry lah. This part over here is actually not covered in your syllabus. It's just for your general knowledge. Okay, but for common sense, you cannot tell. We cannot see with naked eyes how the packing is being like inside the pencil. So the pencil itself, your pencil that you use, so-called the pencil lead, is actually graphite. So this point here, point 3, perpendicular or parallel, not to worry. You just need to remember they are electrical conductor. We won't ask you whether perpendicular or parallel. Okay, so they are electrical conductor because of this delocalized electron enough. Okay, then point 4, they are van der Waals forces between the layers, but within the layers is covalent. Okay, so they have high melting point. Can you see? When we talk about melting point, we don't focus on the van der Waals forces. No, we talk about the covalent bond now. Okay, don't waste time. We'll talk about the van der Waals forces between the layers. Okay, even though it's true, you can break all the van der Waals forces before you break the covalent bond. But we focus on the strongest bond possible. Okay, so can you see that in the lab? Sometimes your graphite, you can see crucibles which are made of graphite. Really very strong because of the melting point. Okay, so this is the uses of graphite. You all should take note in case you're asked. State 1 use crucible. Crucible is just like your you see it in the lab, a bit like the evaporating dish like that. But it's just some lab use ceramic one. The very strong those that can withstand even higher temperature is made of graphite. Of course, it's more expensive. Okay, so that is for molten metal. We seldom see it in the O-level, A-level lab. Okay, I don't think any school will buy that. Nobody does this kind of thing in our school lab. Okay, we are melting the metal. Okay, next one, point 6. So the van der Waals forces, this is where van der Waals forces come in. You remember, they can use it as is soft and used in pencil and lubricant. Okay, so I don't know whether you all notice or not. Graphite is a dry lubricant. Whenever I teach this, a lot of students got shocked. No, I say, huh? Then I say, why? They say lubricant. I thought it must be liquid. No, lubricant can be solid. Graphite is a dry lubricant. Okay, so it doesn't mean that you see those you use on the bicycle, WD-40, all those lubricant that we commonly know because we see them from young. Your bicycle chain rusty, not working very well, you spray the WD-40, all those are liquid lubricant, you're right. Okay, so I don't know why the lubricant is being linked to liquid. That is not true. They are dry lubricant. Graphite is one of them. So graphite, you know how to use it. Just share with you some info. You carry a graphite. If let's say your zipper, the zip on your shirt is not working well, right? You run your pencil through, not the mechanical pencil, the real pencil, 2B or 2B pencil. Those that you need to sharpen. Okay, you run the graphite through the zip, then your zip will work very well. Don't need to spray oil. So nobody will do that. Spray WD-40 on the zip. Okay, you use a graphite, you pull a few pumps, then you can see the zip will move very well. Your zipper. That is one use of graphite. Okay? Okay, so this is a summary table. So we went through all this. Okay, so you can see that this page over here is an overview of what you need to know for the types of substances and how you link to their bonding. Giant metallic bond compound, giant ionic compound, giant covalent compound, and simple molecular compound. Okay, so altogether there are 4 different kind of compounds that you need to. Okay, so you can read from here. So these are the structure, the bonding, okay, physical state. Okay, so this one you can go through. Okay, so except for mercury, this one I don't know whether you're aware. This one, sorry, okay, so physical state, this part here, solid. I think most students remember metals are solid at room temperature, except for mercury, which is a liquid. Okay, this part here is something that's very interesting. If you all watch the movie Terminator, supposed to be made out of mercury, and there's one scene he got shot in the head, right? Then the whole fella collapsed into one puddle of metal liquid, right? Then the person can reform back again. So the director during the movie said, oh, because this Terminator, this alien is made of liquid mercury, that's why he can do that. He can actually melt as in the sense then go under the door and reform on the other side. So next time you watch all this movie, then you can question yourself whether does it make sense or not. So in the sense, it makes sense. Actually, the person knows his chemistry quite well. There's only one metal in your entire world that behave this way, mercury. This is mercury. Okay, this is seen in thermometer, but nowadays no more already. They phase out mercury thermometer because mercury is toxic. Okay, so nowadays you see only alcohol thermometer or data logger. All right. Okay, so we went through all these melting point, boiling point. Make sure you know how to explain, and then the hardness, solubility, and then the electrical conductivity. All right. Okay. I'll leave this for you to read. Let's go straight back to our tutorial to finish up the chemical bonding. Okay, so this is your where is it? Okay, let me push this one to this side. Okay. Oops. Is it correct? Okay, let me open up another. Okay, so this is question 16. Question 16 first. Okay, let me pull out the question paper from. Question paper, yeah, this one. Yeah, correct. Okay, so this is the tutorial question. You all look at the question 16. Okay, question 16 over here, we are talking about over here. Okay, sodium chloride. Chloride is dissolved in water. K ion, N ion surrounded by water molecule. This is the ion dipole attraction, remember? So last week we established in order to dissolve a substance, you must remember we call it solute. In short, we call it solute. The solvent-solute interaction is where energy is given out. This energy must do 2 jobs. Okay, I repeat again. In short, whenever you read, every time you discuss solubility question, always remember how to approach it. The energy given out during the solute-solvent interaction, it can be ion dipole, it can be hydrogen bond or whatever. The energy given out must be enough to overcome the energy needed to break the solute-solute as well as a solvent-solvent bond. Okay, in very simple terms. If you can break, the fella dissolve. If you cannot break, the fella will remain in its original state. So that is what we will look at whenever we talk about solubility. Okay, so in this question, same thing. You see an ionic compound dissolved in water. From our knowledge, we know it confirmed will dissolve, right? But why it dissolved? That is because of the ion dipole interaction. So let's take a look. Okay, so this is how we explain. So you can see that we are talking about identify for the examiner first. They are ionic compound. So there are ionic bonds between sodium and chloride ions. Okay, ClO2 minus is chloride. Okay, so after that, your water is a simple covalent molecule with hydrogen bond. Okay, when they dissolve, right, they need to form ion dipole interaction. Okay, so we have drawn this for you. This is called your ion dipole, right? So can you see this is a dipole over here for the oxygen, and then you will therefore be attracted to the Na plus, delta negative and positive cation, delta negative and the positive hydrogen. Oh, so when you draw, you must draw it correctly. Yeah. So I don't know why sometimes in exam I notice the students just anyhow whack the water molecule. They say ion dipole attraction. They draw hydrogen dipole attraction to sodium ion. That is wrong. No, positive, they don't attract. Also, you can see this diagram. Positive one over here is sodium. Sodium is attracted to the negative end of water. Chloride, on the other hand, is attracted to the positive end of water. Also, draw correctly. This diagram is not anyhow draw surrounding it, and that's it, you call it ion dipole already. Or you must make sure you draw it, indicate the correct attraction for the two ion and the water molecule. They are attracted in this manner. Then we call it the ion dipole attraction. Okay. And so this is how energy is sufficient to overcome the ionic bonding and the hydrogen bonding between water molecules. So again, like what I mentioned, when your solute solvent energy is greater, okay, I put here enthalpy H to represent the energy given out, is more than the enthalpy for your solute, which in this case is your dipole, right? Plus your hydrogen bonding of your solvent. In this case, water is hydrogen bond. If you can do that, it will dissolve. If you cannot do that, it will stay as original form. Okay, simple way to explain. So keyword is sufficient energy to overcome. And okay, let's go on to next question. Additional question here. So over here you have lithium fluoride, cesium tetrafluorosilane. Okay, so we reference to their chemical structure. I think over here you can able to identify this ionic compound. So you must see every time during exam, don't panic, no. Okay, use the data, write symbol first. This is ionic compound. This is a metal. This fella is a SMC, simple molecular compound. Okay, or simple covalent structure. Okay, so you can explain number one area, correct or boiling point. Then we expect it to be barium to be higher than cesium. This one how to explain? Got to do with the strength of the metallic bond, which got to do with the size of the ion, correct or not? This is a very common question. In fact, I noticed O level, they start to ask this kind of question already. O level, they start to ask questions like this to encourage students to understand, even though they never learn about atomic radius. Okay, so this part here, you must take note how to explain. You shouldn't be surprised, okay, because metallic bonding got two areas. Number one, most people are able to explain. When I ask them sodium and aluminium, right, why aluminium has a higher melting point, they are able to tell me because there are more valence electron for aluminium, right, compared to sodium, Al3 plus and Na plus. So we know the aluminium melting point is higher because the C of mobile electron, they are more compared to sodium. Every sodium ion give up 1 electron, but aluminium give up 3 electrons. That one no problem. I think all the students can answer that. Okay, but this kind of question, when barium higher than cesium, you must look at the position of barium and cesium in the periodic table. Are they in the same? First question you need to ask, are they in the same group? Yes, no. If they're not in the same group, where are they? Which one is larger? Then from there you can answer it. So in this case, we want the atomic radius to be as small as possible, right? And your atomic radius is small, then your attractive forces for the electron is stronger, right? Now you want to pull the electron towards yourself. So in the sense of metallic bonding, this is good. This is actually enhancing the strength of metallic bond. That is what metallic bond is about. Metallic bond is the electrostatic forces of attraction between the ion and the sea of electron. So you must think deeper. How can metallic bond be made stronger? There are two ways. Number one, size of the ion. Number two, number of electrons. More electron, the better. Correct or not? Because all directional, you got electron, and your aluminium 3 plus in the first place is very small charge density. With the high charge density, the Al3 plus compared to Na plus. Remember, across a period, the ionic radius start to decrease, right? Because they are isoelectronic. Okay, isoelectronic, same number of electron, but the number of proton increases from left to right. Okay, so that one is for aluminium and sodium. Okay, so later we see for this part first. Then part B, describe why lithium fluoride is soluble in water. Or similar to the question above. Okay, so ionic compound, why is it soluble? Okay, let's take a look. So this is how you talk about lithium fluoride. Okay. Lithium fluoride, point 1. So guide the examiner through. Tell me first what you identify is an ionic compound, giant lattice structure. Then you talk about all the strong electrostatic forces. Number 2, cesium. Number 3, your silicon fluoride. Silicon fluoride is a simple covalent compound. So there's only dipole-dipole moment. Okay, ID kind. If you resolve the dipole moment, this fella is non-polar. So it's ID. There's no PD here, right? So more energy is overcome the ionic bond and metallic bond compared to the weak interaction between your silicon fluoride. Okay, so that's why you can see that they are in a class of their own. These two, the bonding point is super high. And this one super low. Because it's intermolecular forces for the third one, and then covalent metallic bond for the second one, and the first one is your ionic bond. All right, so you can see a question like one, I can tell you by A level, right? Everybody will be preparing for this question. Okay, so there's no room to make mistake. So when you're explaining, always remember what I say, straight to the point. Or don't go one big round. Silicon fluoride, tetrafluorosilane, SiF4 is non-polar. Therefore, there is only have ID. Don't need. We never ask you whether polar or non-polar. Okay, straight away go right into the question. Or you can identify is weak. ID, you just mentioned that, and then contrast between the other two structure to score your full points. Simple as that. Any question first? So it's a typical question, but you can see it built on your O-level knowledge. At O-level, we usually ask you compare two of them, two substances, but now we got 3. Okay, this question can also take a different twist. Like for example, I give you 2, right? Then the last one I ask you predict, explain. Something like that also can. So it's under your essay question. Okay, so you're likely to see this question for your essay kind. Promo, you will see it, definitely. The reason is because you don't have enough topic to test your. So your promo exam, you're likely to see this question. Common test or promo. Okay, bonding question. Okay, A level depends. Okay, depends, but if it come out, it will come out like something like this. Okay, or a data response question. All right, next, suggest why you expect it to barium to be higher. So they are both metal. So barium has a greater number of valence electron compared to cesium. Okay, so your cesium have stronger electrostatic forces between the cation and the valence electron. Okay, so let's take a look. Where is barium? Hold on my periodic table. Okay, barium you can see is in group 2, right? Then your cesium is in group 1. Okay, group 1 can. So the difference in the atomic size are not as big. Okay, so maybe this one again you can use the just similar to your this aluminium versus sodium story. Same. Okay, I will want you to change it to barium, maybe barium versus magnesium. This one I think better. Barium versus magnesium. Okay, can. So that's how I tell you. 2 ways they can test you. This is number 1. This question belong to number 1. The number of delocalized electron increases, right? The metallic forces, stronger electrostatic force attraction, because all directional you have valence electron, a lot of them. So you have more compared to sodium, right? Aluminium and sodium. So cesium and barium, same story. Barium is period 2, group 2. Cesium is group 1. So barium got one additional electron per ion. You all know cesium and barium group 1 and group 2 and group 1. So same story as aluminum and sodium. So I put a 1 here so that you all can review. This is number 2 that I think you need to prepare. If they ask you predict barium and magnesium, I was surprised that not many candidates know how to explain. Number 1 is covered extensively in our notes. Number 2 actually got to link to the size of the atomic radius. Barium and magnesium, barium is larger compared to magnesium. So the metallic bonding for magnesium, right? Metallic bonding strength is likely to be stronger, smaller ion. Or you can actually look at the charge density. Magnesium has a higher charge density compared to barium 2+. That's why it will pull the electron closer to itself, and therefore the stronger the electrostatic forces of attraction. Hence, we expect magnesium to have a higher melting point compared to barium. Can you write down somewhere? Compare this to scenario 2. Scenario 1, I think quite simple. A lot of questions always test like that. Okay, so that one I'm not worried. Atomics, this one got to do with the size of the ion, size of the ions. Okay, higher charge density for magnesium compared to barium. Higher charge density. I shouldn't use the word charge density alone because they are both in group 2. Higher charge density. One of them is 2 over smaller size for magnesium compared to barium. Barium is larger. Stand by. 2 ways they can ask you. So I give you the 2 ways. For metallic bond, you must remember that. Okay. All right. Okay, so now for barium and cesium, then you may ask who got higher charge density? Doesn't matter. They are both in the same period. You remember in the same period, right? The difference in size are very negligible. Even though you have barium and your cesium. Okay, of course you can look at the size itself. You can also tell barium is a slightly smaller size compared to cesium, because your barium over here is Ba2+, cesium is Cs+. They have the same number of quantum. The number of quantum shell for cesium and barium is the same, occupied quantum shell. The only difference is that your barium got one additional proton compared to cesium. Cesium then followed by barium. You see your periodic table, group 1 and group 2. So barium have one more additional proton. So therefore the ionic size for barium is slightly smaller than cesium. A bit smaller, that's all, compared to your cesium. Very little only, okay? So you are right to say that barium, even if you tell me barium has a slightly larger, higher charge oversize, right, then your cesium is not wrong. It's true, that means the size itself, okay? But in this factor, the electron, the number of delocalized electron is a more important factor because they are short of. Every cesium is giving out 1 electron, barium is giving out 2 electrons to form the sea of electrons. So barium got double that of cesium. Okay, so this is true, just like aluminum and sodium case. So this is just a normal, typical question testing on the strength of metallic bond. Okay, right. Next one, lithium fluoride soluble in water. So same. This one I think you all can answer very easily, right? Ion dipole attraction, energy given out more than enough to overcome the ionic bonds, the ion-ion interaction, and the hydrogen bonding between the water molecules. That's why lithium fluoride is soluble in water. The diagram is below. Can we move now? The diagrams are there. Draw carefully, okay? Drawing, not suka-suka, just look like the thing. I've seen question student draw like that, no? Just like that. Then they put like that. Actually, they know or don't know, I also don't know. Cannot tell. What is this? You cannot tell because the orientation of the dipole is very important. It's not hydrogen attached to the fluorine or oxygen attached to the fluorine. I cannot tell. Just by drawing one molecule like that, then you tell me this is a ion dipole interaction. it's not sharp enough. Even though I understand that the student probably, the candidate knew what he's talking about. But I feel that the diagram drawn this way is not sharp enough because it's not clearly showing that the negative to the positive side. Then it makes sense. Can you see? Delta positive, delta, positive to delta negative atom, and then the delta positive hydrogen to the fluorine, and then you call this ion dipole attraction. They are attracted to different parts of the water molecule. That's why the orientation is different. You can see the Mickey Mouse here. The face of Mickey is attached to lithium, but the ears of the Mickey is attached to fluoride. All the orientation of the water molecule is different. Also, that's a reason. By drawing this, we cannot tell. No? The one I put a question mark on the right-hand side. Really cannot tell what is the candidate thinking. So you end up, some examiner give marks. Some examiner will very picky one and say, actually, this student understand what is ion dipole or not. Very questionable, and you cannot give any credit. So be very careful. All right, let's go back to the question. Next one, organic compound. You can see this is linked to your chapter of organic compound. So if you ask me currently at this stage, right, based on your O-level knowledge, I think you can recognize 3 of them. Okay, recognize 3 of them, at least 3 of them. This one is an alkane. You see, this fellow is alkane. So you write down first. This one is also alkane. Can you see or not? Then you may ask me, how I know it's not alkene? I observe the number CH3, CH2, 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 CH3. If there's an alkene, right, cannot be CH2 inside one. Confirm it's CH somewhere. Then there's a double bond. No? So this is some trick I teach you, 2 of you. Observe. Okay, observe, then you know whether it's alkane or alkene. B, I know it's alkane. How I know? You can see a 4 here and a carbon here. This carbon got 4 bonds. There's no room for double bond. The rest are all methyl group. So it's a carbon attached to 3, 4 methyl group. This is called a methyl group, CH3. Like that? So you must observe. Then you can see a lot of things inside the formula. Even it's given to you this way. I can see that which family it belongs to. Can you see this fella? This is new. You haven't seen it yet because you haven't covered organic chem. This is a ether family. Can you see a R group here and an R group here? A ether family. Okay, like that one is ether. 2 carbon joined to 1 oxygen, the center is an ether. Okay. Next one, I think you should be familiar with this fella. Is an alcohol. 1, 2, 3, 4 butanol, right? And alcohol, butanol. Just give the general name first. Okay. The other thing I want you to observe, right? You see A, B, A, C, C, and D. Focus on the question itself. They ask you for similarity and the differences in boiling point. Okay, so you have relative molecular mass and 2 boiling point over here. So this part here, these 2, they are the same. Alkane discussed together. Okay, you see the question is always in this mode one. They don't compare. They want to compare apple with apple. You know that this got to do with the sausage, and not the sausage, the hamburger and the sandwich story. Remember I told you, right? Surface area, yes, the area of overlap. Confirm I use that to explain for A and B. And then for A and C over here, right? You can see that the MR is about the same, but here got 1 oxygen. So very interesting. Over here got 1 oxygen, right? There could be some kind of PD over ID kind of story to explain this part. And then C over D, here got hydrogen bond. No? So you can see the strategy. Whenever you see a question like that, right? Roughly, you must know the strategy to explain. And then when you explain, it must make sense, right? So this is how our approach should be like. Okay, so let's take a look. I think we went through this question last week, right? Did we? We went through a bit, right? But I think I haven't unpacked this question fully. So now we can see. Okay, so you can see for part A and B is the sausage and the hamburger story. Not the sandwich, not the sausage. It's the hamburger and the Subway sausage, Subway sandwich story. So your hamburger is like that, right? You see, surface area overlap very small. That is your B. Because a ball shape, when two of them mix to each other, right, you will have lesser extent of overlap. Then you come to A, right? A is linear. Then you have this, the subway sandwich. You see, intermolecular forces, surface overlap increases larger compared to B. Straight chain. Branch, you have lesser surface area of surface area that is smaller compared for B, that is overlapping. So your ID is greater for A, more energy is needed. Or keep it clean, okay? Don't overlap things like don't overlap the things like the strength of the covalent bond, blah blah blah. They are the same covalent bond inside. Anyway, we are not breaking covalent bond. Okay, so talk about the very what you call that, the very key reason to explain boiling point different. All right, okay. So that is your A and B. Okay, don't worry, we will not ask you to name because right now you don't know the name of A. Just call it A and B will do. Okay, so don't need to what pentane, 2,2-dimethylpropane. You haven't reached organic chem yet. Oh, don't worry about that. Okay, so this is surface area. Okay, then after that we go on to A and C. Can you see A and C? One is polar, one is non-polar. There is ID, and PD. So let's compare. The MR is almost similar, 72 and 74. So the boiling point is almost the same, right? So by right, we expect your this PD to have a higher boiling point. But remember what I told you last week, right? The molecular mass factor is more important. The very overriding one is even more important. So that's why you can see that the MR for this 74 and 72, and yet the boiling point is lower than 36. Okay, so very close in a sense. Okay, so this is how we explain. Similar boiling point, simple covalent bond, even though one of them is ID, the other one is PD. Okay. This is got to do with the MR closeness, the relatively similar MR. Oh, okay. By right, like what I say, right? By right, if you let's say you have a compound with similar MR, right? One of them is PD, the other one is ID. We expect the PD to have a higher boiling point. But in this question, is very interesting. You can see from the data itself, right? Even though the PD one, the MR is a bit higher, the boiling point is a bit low. It's a bit lower compared to the ID, the compound A. So you must remember to reframe the whole answer to suit the data. Okay, so by right we expect C to be higher one. You are right to say that, no? C to be higher, right? Correct, no? Because this two is 74, this one is 72. You see, this one is 72, this one is 74, and some more. This fella is PD. But how come the boiling point is still lower than that? So again, like what I say, data given to you, you have to explain according to the data. Data not given to you, ask you to predict. Then you predict which one, C to be higher than A. You understand what I'm talking about, right? Okay, let's say the last column not given to you. Last column, this boiling point not given to you, right? If you ask to predict A and C, right, which one have a higher boiling point? What will you say? C will have a higher boiling point. Imagine you never see column C. Okay, but the thing is that what I'm trying to say is that PD definitely stronger than ID, but a bit. Okay, so because the MR is still higher than A, it's not wrong for you to say that the boiling point for C is higher than A. You must know where I'm coming from. If you are asked to predict, you can predict that C is bigger than A. Why? Because it wins in two categories. Number one, MR is higher, a bit higher, 2. Number 2, it is PD. We know PD is stronger than ID. So if you tell me the boiling point for C is higher than A, it's not wrong. Okay, but this world is not perfect. So when they show you the data, right, you must explain according to the data, no? So I have seen candidates during exam, write down there the data is wrong because PD is stronger than ID. There is a mistake in the question. There's no mistake. These are real data. So remember what I say, whenever a data is given to you like this question, right, you must tweak your thinking to suit the data. Okay, so you can see that in part answer here. Can you see what I explained? Is ID, is PD, right? So this is correct. Can you see the oxygen? You refer dipole moment, one oxygen there. For ether is PD, this is ID, right? So these 2 points, no problem, no? Then part C is the one that you must understand. The data show you in this manner. So you know that this is an exception, so-called the anonymous or exception to the rule. Despite having higher MR and despite being PD, the boiling point is still lower. That's why, but we didn't say lower a lot. They say similar boiling point. Okay, right. So that's why we say that they are similar. They are not the same. They are similar. Okay, so you must learn what I call this exam technique, exam skill. Okay, so you must learn how to tweak your answer to fit the data. Okay, don't go against the data. Okay, it's just like going against a trend, right? You know the water is bringing you out to the high sea. You follow the sea, you swim against the current is very difficult, right? So you follow, but it makes sense. Okay, that's why there's always exception to the rule. Okay, if let's say this question asks you for prediction, if you tell me C has a higher boiling point than A, okay, what? Nothing wrong, because you are going in a line with the theory. You have never seen this compound before, you ask to predict. Imagine you don't see column C, the boiling point data. If you predict that C is higher than A, I won't mark you wrong. You're right, because MR is higher and it is also PD. So you will tell me C boiling point is higher, let's say 40 degrees Celsius. Is that correct? Of course. Nothing wrong at all, because you have never seen this compound before. You're not expected to memorize boiling point. Oh, cannot? So Rachel, you understand where I'm coming from? You understand where I'm coming from, right? So when you read the answer, actually doesn't make sense. I thought PD higher than ID. You're right. Nothing wrong with what you have learned. Correct one. MR factor and the PD factor. Right or not? Number one is MR factor. Number two is the PD greater than ID. You're right. No problem. But this question asks you to explain data, not predict data and explain. Okay, not ask you to predict boiling point. So you must tweak the question answer to fit your need. Okay, so despite difference in MR and also point 1 and point 2, they are quite similar. So therefore, the boiling point are similar. Okay, we never use the word same. They are different. One is PD, one is ID. Okay, but that's the best way to wrap up this question. Or don't go and write one big chunk there. The data is wrong. There's a typo error. Okay, then you say that ask the invigilator, can you please check the boiling point correct or not? Then you cannot sleep. So don't do that. Use the data, revert the thing, and then explain. Unless you're asked to predict. Okay, so different. Predict is different. Predict, I will expect you to predict is higher. Okay, so remember that. Okay, next one is hydrogen bond and ethoxy ethane. Okay, first you explain they are both polar. Okay, C has PD, ID. D has hydrogen bond, extreme end of PD. So don't need to fight. No fight already. No fight. D confirm higher boiling point than your C. This one very clear cut. Even though you look at the MR, you see the MR 74, right? MR cannot fight against hydrogen bond unless it differ by a lot. Unless one of them is 100 plus, the other one is 74 hydrogen bond. But in this case, the MR is the same or very close. Hydrogen bond is definitely the outstanding critical factor. Again, don't go against data. Like what I say, don't go against data. In exam, let's say they give you C and D. They tell you that C, right, is 125 PD. boiling point is higher. Then the other one is hydrogen bond, let's say 36. Hydrogen bond. Then you say hydrogen bond confirm stronger than PD. Something wrong with the data. No, the MR factor outweigh the hydrogen bond factor. Or there are two factors in play here. You must remember apple and pear. You know, so if I ask you compare one apple and one durian, you cannot compare one. You say, well, I know that this the hydrogen bond in this compound is very strong. By right, the boiling point is higher. Nothing wrong with that, but remember the MR factor, if it differ by so much, 3-4 times larger, one durian and one apple, you cannot fight against the relative strength of the PD and hydrogen bond anymore. Okay, so just answer accordingly. The MR factor is more significant. Okay, therefore the boiling point is higher. Don't talk about hydrogen. I mean, you can talk about hydrogen bond, but you must end off your statement with that the molecule is larger. Therefore, the van der Waals, I mean the PD is more extensive compared to the hydrogen bond. You need more time to overcome all of them. Okay. Okay, let's go back to the question. Okay, any question first? 2, okay. 2 is a question. I call it data response question. Then you must know how to tackle. Okay. Okay, question 3. This is the reducing agent. And given that it's central atom, draw the dot and cross diagram and predict each of them. Okay, so have you drawn? I think we've drawn this before, right? We have drawn this before. This is 3. Okay, so just check the answer. No problem. Dot and cross diagram can. The first one, the mother shape is tetrahedral. There's one bond pair there. Okay, so it's trigonal pyramidal. ClO2, one lone pair here, the mother shape is trigonal planar. And then your this actual shape is band shape, V shape. And then ClO3, you have your tetrahedral again, and bond angle is 107, trigonal pyramidal, actual shape. Or negative charge give to the more electronegative atom. Okay, and all right, there are some additional questions below. Okay, let me see. We can go through this when I will add to your revision for your common test instead. Let's go on to the new chapter. Shall we? Chem. You'll be tested on thermodynamics, right? After school you open common test, if I'm not wrong. Or can you pull out? Let me close all this first. Can you pull out your Chem? Not Chem. Yeah, Chem, right? Enthalpy change and so on. Okay. Okay, let me close all these first. Okay, here energetics. Okay, this one I can close it. Okay, you all have this copy, right? Two of you have this copy. Energetics. Okay. Yeah. Okay, like what I say, I give you an overview because you all have done your lecture in your school already, right? There are a lot of definition inside. Okay, I tell you, those definition that your teacher teach you, right? Temperature of formation, change of hydration, temperature of solution, so many lattice energy and blah, 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 okay? Is knowing how to use them that is more important, okay? The definition help you determine because it's very clearly stated. For example, lattice energy is 1 mole. Enthalpy change of formation, 1 mole. Enthalpy change of reaction, 1 mole, something like that. Okay, all this information is embedded inside the definition. That's how we build all the definition needed for this chapter. So for this chapter, there are 2 things to take note of. One is the definition. The definition allows us to come up with the enthalpy changes and know what the question is talking about. Okay, then after that, you will definitely draw 2 things: energy cycle and energy level diagram. You must practice. Okay, you must practice because when you don't do enough, right, you get very rusty. Especially when you reach year 2, right, then you realize, hey, how come I don't know how to craft the energy cycle again? Okay, but there will be some tricks I will teach you along the way okay, how we approach this kind of question. Okay, you notice that the way that I teach some of this, how to do the energy cycle may be a bit different, okay, but don't worry, there's no right method or wrong method to do the energy level diagram, but you must have some awareness. Awareness means when you draw the wrong one, you will know. Okay, and how to check, you will know. Okay, later I'll teach you how we do that. Okay, so let's take a look at this copy. So you can see that this is an endothermic exothermic reaction. Okay, so I think hopefully you know by now. The enthalpy change of products is lower than reactant. So this box here is to draw this enthalpy change diagram. Okay, energy change diagram. So can you use a ruler and let's draw together? You by this pen. Okay, draw the axis first, right? So your energy lower than the reactant is exothermic, right? Go up the mountain, come down. So this is energy. This is progress of reaction, POR in short. This is energy. Okay, so you can draw yourself. Here I'm going to label the important data. This is called your EA. Activation energy, dotted line across if you want to be more exact. Here is enthalpy less than 0. Come, you draw. O level you drawn before, so shouldn't be a problem. Okay. So of course we haven't reached the chapter on rate of reaction yet. Rate of reaction we talk about two things. There are catalysts. There are two kinds of catalysts. Okay, so catalysts can lower the EA. Okay, so when we reach a chapter, then we'll revisit this drawing with catalyst. Okay, so currently we don't deal with catalyst. So normal one. Okay, so first draw POR, your energy. You all have ruler. Your line should be sharper than mine. Go up, come down. Okay, enthalpy change. This is your EA. Reactants and products. Okay, so you can add here reactants. Here is your products. Reactants and your products. Okay, clear? Can easy. Okay, this is your endo and exothermic. Basic you must know. Okay, that's why the sign is more than 0 and greater than 0. Okay, remember in the diagram, I don't know whether your teacher have taught you all before. Single arrow, there's no such thing as double head arrow. Enthalpy is very clear cut. Single head arrow up and single head arrow down. So whenever you draw, don't use double head arrow. You will penalize. Okay, for nothing. Okay, so enthalpy change. Okay, so you can see what is enthalpy change. Okay, so I leave it to you to read. Okay, so the negative sign is exo, positive sign is endo. So this is what we actually talk about, the standard enthalpy change over here. So standard enthalpy change is measured under standard condition. Temperature is 25 degrees Celsius and pressure is 1 atm. I think this part your teacher have covered, so I won't go through this. I just want to bring you through the definition in a table form. The exact one is inside your notes. Okay, so this is just a definition of what it meant by enthalpy change of formation, representation. Okay, so let's go through one of each of them. By now you should know, you can see a small f there, enthalpy change of formation, right? So this is the formation of the elements in the standard form. Standard form means, example, water, right? So it's H2, then you are given the standard formation in the standard form, compound, and then per mole of compound is 1 mole. So it's hydrogen here plus oxygen. So over here is gas. This one is gas, right? And here is half. You must get used to half. I know it's not natural at A level because you all say, wow, how come got half? I thought O level always seem as whole number. No choice. The definition of enthalpy of formation is formation of 1 mole of the compound. For the formation of 1 mole of water, you only need half a mole of oxygen. Stick to the definition. Okay, so this is per mole of the formation of this compound. So this is the first one. Combustion, again, same thing. The substance plus excess oxygen. Can you highlight this word? Okay, why? Because when you talk about combustion of carbon, confirm is carbon dioxide. Carbon dioxide, there's no CO. Because the definition already says excess oxygen. If they want to test you on CO, right, then they must give you enthalpy change of formation or CO. All this is always a question over the years. I keep answering many times to my students. Then they cannot understand. I talk about incomplete combustion or complete combustion. Yes, you are right. Incomplete combustion is CO. Complete combustion is CO2. But in the definition of combustion, you already put down there in excess oxygen. So you're very clear cut when you ask you combustion of carbon is what? Carbon dioxide or CO2. Okay, so remember combustion of the oxygen over here, let's say carbon plus oxygen, right? Burn completely to give CO2 one. Okay, per mole of the substance, combustion is 1 mole here. Okay, so CO2, the gas, standard form. Standard form means room temperature. Okay, next one, neutralization of water, acid and bases. I think this part you'll remember is negative 57.3. You see this value, MCQ, right? Confirm is a strong acid, strong base. No need to worry. Confirm is strong acid, strong base. Anything below that, one of them is weak. I repeat again, you see 57.3, magical number. You see this number given to you, right? Confirm the two unknown. Now, whatever acid given to you, they say unknown acid, unknown base, right? It is a strong base or it's a strong acid. Only strong base, strong acid will give you negative 57.3 kilojoules. Okay, the rest of them will be lower. There is a weak acid. Okay, so that's why it's less exothermic. Less exothermic means smaller than 57.3. Example, maybe negative 40.2, 42.3, and so on. Yeah, Rachel?
For the strong acid or base, right? So it can be one strong acid and then one weak base, but still have...
both of them must be strong. Both of them must be strong, yes. Yeah, both of them must be strong. If they are not, one of them is not strong, right, then you cannot get 57.3. And they already pre-calculated already. All this bond breaking, bond forming, in all the literature they call it, then they already tested all the strong acid, strong base titration, right? Neutralization energy is 57.3. So magical number, okay, 57.3. Last time we used to do it as 57.1, but the data keep changing. So I think the more accurate one you all know nowadays is 57.3. 57, the first two number confirm 57. Okay, 57.3 for your currently. Okay. Okay, next one, atomization. Atomization, you must remember this part here. Okay, I went through 1, 2, 3 already. I will tell you what are the areas that we will always go through. When we will go through, right, you must remember. Element is the standard form to form the atoms of the gas. Okay, so that is your atomization of the element. Okay, so for example, atomization of this chlorine. Okay, so you are actually converting single 1 mole of the atom. Okay, so you will actually look at chlorine is a gas, right here, over here, right? Then you all ask, obviously, chlorine is a gas, chlorine is a gas, but at room temperature is a diatomic element. So you are looking at this, right? Cl2, half of it, gas, change to gas. So again, it's not natural one. That's why this chapter not natural. It's not natural. It's not very instinctive to us because we have been calling. We always look at chlorine gas as Cl2. Then now they got this atomization. Okay, you need to use that in lattice energy calculation. I repeat again. This one is needed in lattice energy calculation later. So you must remember. Okay, atomization. Atomization of compound. Okay, this one also have. So same thing, so water atomization, right? So this is your H2O liquid all the way to H2O gas. Okay, so it's this one. Of course, your atomization of compound, you also have other form. Let's say other compound, you can have NaCl or whatever. Okay, but very rare. Okay, very rare to see that. Okay, atomization, if let's say you change from a solid, I give you an example here. And you read some literature, you see this term. What example? Okay, here. Let's say calcium solid to calcium gas. Can you see? This is atomization of calcium, right? It's also known as sublimation. You all can write down another term here. Enthalpy change of sublimation. Okay, in case you come across in the literature, you read some books, then you say, hey, I thought this is atomization, you're right. But if it's solid to gas, you can also call it sublimation. Enthalpy change of sublimation. And so just give you some additional info in case you see this term in some textbook in the future, then you don't need to get stunned. It's actually referring to this one. So I put a star here. Okay, don't anyhow use. I repeat again, don't anyhow use. Can you see? This is calcium solid change to gas. That's why I use sublimation. If it's a gas change to a gas, it's not sublimation. So it's different. So this term over here, you must remember what you're looking at. Those which are solid turn to gas, yes, sublimation. Okay, right. Then the next one, bond dissociation energy, Be. So bond breaking. So this is always positive. You need energy to break bond. Okay, for gaseous species. Okay, later we want to use that also for calculation. Okay, next one. First ionization energy. This one you must remember. All your lattice energy calculation all involved is. Okay, so your Mg to Mg plus, then Mg2 plus before they can form the compound again. Okay, first IE, second IE, then your electron affinity. Electron affinity we've seen before, right? So this is talking about the non-metal. These are the metal. So you must know what you're looking at. These are the metal. All these here are for the non-metal, Nm. Okay, no, doesn't make sense to have, let's say, magnesium electron affinity. Magnesium don't take in electron. Magnesium give out electron. That's why this is for metals. These two are for non-metal. Electron affinity. Again, we are going to use them inside the lattice energy calculation. Okay, so it's all related to this big boy here. We call it the lattice energy. Okay, so later we see our Born-Haber cycle. We are making use of all these data in the calculation. Okay, next one, hydration energy and the solution. So this is related by this formula. Okay, I think it's not new to you, right? Enthalpy change, I think your teacher will probably give you this. Lattice energy is hydration energy. Remember, hydration energy just now we discussed in ionic compound. Energy given out when the water molecules surround all the ions, right? Hydration energy, right? Minus away the enthalpy change of solution when this compound fully dissolve inside the solution. Okay, so we are going to see these three together in our calculation later. Lattice energy, that is the meaning of lattice energy. Okay, I want to highlight to you what. Okay, lattice energy. Lattice energy, right? Can you see? Lattice energy is always negative, right? Because you are forming bonds. Forming bonds means you are forming bonds, energy is given out. That's why it's always negative given in your data booklet. In your data booklet or in your data that's given to you, they always report it as negative. Okay, but in the energy cycle that you draw, right, look carefully how you are drawing. Okay, so if you are drawing from the ions, right, from the sodium, let's say for the ionic compound to the ions, right, you will follow, you can invert the arrow and change the lattice energy to positive one. So you understand what I'm talking about. Going forward is negative, right? When you form the compound, that's why in the question paper, when you see lattice energy, right, they are always talking about negative because it's forming. Forming is always negative. But when you use it in your Haber cycle, right, Born-Haber cycle or blah, 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 anything else, look carefully at your arrow head, which direction is going. So it is okay for you, right, to use a positive one in your energy cycle if you need to. Even though when you report lattice energy, you always report it as negative. So this is something that you need to, at the back of your mind, you must remember. So be a bit more flexible when you use it, depending on what is the reaction you're talking about. Because you think about it, right, lattice energy is the energy given out when the bonds are being formed. So if I want to break the bonds, what is the energy needed to break the bond? It must be the same magnitude as the lattice energy, isn't it? Just the only difference is that the positive sign in front. That's all. So when you change the arrow head, you change your positive sign. Later I'll show you in some of the examples. All right, so at the back of our mind, take note of these three. When we visit this thing, the three of them are related. Okay, hydration energy, negative, and the enthalpy change of solution. Okay, or lattice energy, this one. Okay, so later then we see this relationship within these three. Okay, right, let's go on to this part, calorimeter. Okay, have you all done this experiment already in the school? Whether in physics, I think you all may have done this before, the calorimeter. They try to measure the change in the temperature when the reaction is over. They use this term, the MC theta. MC theta is the amount of heat that's being involved. Okay, you want to calculate out. Okay, so this is one part of the physics that is related to chemistry in this chapter. Okay, so you need to use the formula MC theta over here. Okay, this is your Q equals to MC theta. Okay, right. So usually in the question, they may give it to you lah. Okay, they may give it to you. I don't know whether you're familiar with this. Okay, let me share with you another diagram. This one. Have you seen this? Let's say a cooling curve. There. They'll ask you to do an experiment, monitor the temperature when you add the zinc, start the stopwatch. After that, temperature start increasing, right? After that, they finish the reaction over, then they'll ask you to cool it down. After they draw this red line, extrapolate up, then you can see what is delta T. Okay, this is usually how you do this experiment. Familiar, right? I think you probably have seen it before, or at least in theory lah. Okay, nowadays I cannot remember whether they still do this kind of experiment. Okay, but because our practical is a chemistry paper, so they will usually do two components. Okay, the QA and the VA is more heavily featured in your practical exam, not this one. So this one is tested in physics. Okay, that's why for physics, you all do physics, you all will do this kind of experiment very often. You all do physics or not? You all compete? You all do physics, don't you all do a bit of bio students. Okay, so my opinion is that because this is covered extensively in physics, they don't want to double test a candidate. They don't want to advantage students who do physics. Because those who do physics, they repeat this experiment again in chemistry, they're going to score double the point. So this MC theta is just for normal practical, they may have asked you to do 1 time or 2 times. Okay, so if you happen to do it, this is how it works. This is how your delta T is being computed. Okay, so don't worry about it. So just to let you all know how this thing is being done. Okay, let's go back to our notes. Okay, so this box here is that. Okay, so your drawing I just show you just now. So this is a graph. Okay, so later you all want, you can replay the video and watch again the graph. Okay, so let's go to the actual calculation. Okay, so this is the question over here. So basically, I think this question may be familiar to most of you in your tutorial. Okay, so they ask you to calculate the enthalpy change of reaction, right? So 1 mole of magnesium. So you calculate MC theta. Okay, you can see that this is 75 cm³ of silver nitrate. So you are told that solution is 1 gram. So I can assume that mass is 75 grams. Right? Okay, after that your theta is given, right? And a specific capacity is given as your 4.18. You see, I extract all the figure first. Then your theta is the temperature change. 19 rose to 27. So 27.2 minus 19.5. Okay, can you calculate out for me X? Okay, so you will be able to get, you can calculate all these later. Okay, I show you how first, okay, because your calculation you can try later. Okay, so you get this value Y kilojoules. Then they ask you what is the enthalpy change of the reaction. You must understand what is rose mean. Rose means rose is not the flower. Yeah, very lame. Sunday morning. Rose means increase. Increase. Okay, so increase means what? Endo or exo? Increase in temperature means endo or exo. Exo, right? Temperature given out. Exothermic reaction. That's why it rose. Temperature rose. So when you use your calculation for enthalpy H, you must remember, introduce a negative sign here now. So Y divided by 0.7. Okay, cannot. You know why? Enthalpy change is per mole. So you must calculate number of moles of magnesium first. 0.7 divided by atomic mass of magnesium, I think. So you get Z. You must remember, so divide by Z. So you divide by Z already, right? Because this is kilojoules, your answer here is in joules. So your answer here, you must divide by 1000 to convert back to kilojoules per mole minus 1. Okay. We won't spend too much time here because generally this portion here is more to understand the formula of MC theta. Okay, so in exam, very few, not many questions will be tested on this way to calculate MC theta. Maybe occasionally you see one part you calculate the energy, but you should know how to do it. Okay, and then to divide by the kilojoules, you solve it. So you can see the tutorial, we also never give you many questions on that. Okay, can you try out later? So based on this, you'll try out later. Okay, let's go on to Hess's law. Okay, this is very important. Hess's law is very simple, right? So I think you all remember the definition. Change in enthalpy accompany a reaction is independent of the pathway between the initial and the final state. Okay, so how to remember is very simple. From Pasir Ris to go to Boon Lay, I can take the east line all the way down. Correct or not? Alternatively, if I have a very itchy backside, what should I do? I take all the way to Yishun and then come all the way down. Do I still reach Boon Lay? Yes. Change a different line. Okay, north south, northeast line or wherever, southwest line. Okay, so you can also reach there. So every route that you take, the energy is the same. Okay, that's what Hess's law is about. Okay, so remember the definition for Hess's law. Okay, the definition, I have never seen it being tested for a very long time, at least 10 years. Okay, because definition question are very low value question. Okay, you ask me, it's very low value question. So this definition has not been tested for super long time already. Okay, but the application, yes, every question need you to do application. Okay, right? So you can use the energy cycle or energy level diagram. Okay, this part here you must remember. This is the one that students are worried about. Okay, I highlight. So you must train yourself because you know that a lot of people are worried about this portion here. Okay, so this one, energy level diagram. This one, I can tell you that this part here is the one that most students have difficulty. Not difficulty lah. Okay, they have this phobia to draw energy level diagram. Okay, so now I will show you exactly how we do it, and then we do the simple one first. Energy cycle, energy level diagram. Okay, so you follow me. A plus B give you E plus F, right? We will call it positioning. Okay, positioning first. Okay, you see A plus B give you E plus F give you C plus D, right? Right now. So there are two ways to do it. Okay, you must central one of them first. Central one of them, I will choose, you can put down E plus F on top. Because I realize that A plus B will give me E plus F, right? Then E plus F will give me C plus D. So I can form a relationship this way. Okay, and this happened to be my enthalpy H according to the question. So I can insert in minus 100 and then positive 200. Finish. Now positioning. It's a skill, that's why you need to practice energy cycle. Start from somewhere, then the rest of the equation will build the energy cycle. Okay, make sure they close up. Eventually, the whole cycle will close up. Okay, energy level diagram, you know how it look like, right? Always remember there's the axis energy. That's why it's called energy level diagram. Okay, right. So remember what I'm going to teach you now. Okay, so first you can see here, A plus B gives you C, E plus F, right? And if I want to put here as A plus B, I draw a line first, A plus B, right? Okay, I must have this. There are two things you need to be mindful of in energy level diagram. Number one, you must understand the sign. Negative means go down, positive means go up. Number two, I must know the magnitude. Okay, I observed this over the years. Why students struggle with this portion, right? Is because of the sign and the magnitude. Okay, A plus B gives you E plus F is negative, right? So go down, negative 100. You have E plus F. You see? So you must be very observant. Negative means go down, right? Then next, I observe something very interesting. This E plus F go to C plus D is 200. Is 200 bigger than 100? Yes. So level 1 is here, level 2 is here, right? Level 3 must be on top. This is the simplest thing that you must understand and master in energy level diagram. Okay, why? Because when I ask students to draw, right, some students draw D plus E, C plus D, right, in between 1 and 2, or even below 2. If you draw number 3, right, over here, below 2, right, that means it's an exothermic reaction. But I look at the reaction is positive 200. It is going up to where? To level 3. Oh, you draw a straight line here, level 3, let's say you draw a straight line here, then you have C plus D. This 1, 2, 3 is a way that you approach energy level diagram. Or you practice your mind to see the magnitude. Or you must train your mind to see this. You see E plus F, how I know it's going up and more than 1 because it's 200. Okay, so this is positive 200. It makes sense. Going up, positive. Magnitude 200, bigger than 100. So it's above number 1. Can you see why I can tell you the law of candidates see energy level diagram? Let's say question say energy level diagram, they panic because they don't know where is level 3. Oh, so you must train your mind to see two things. See this positive sign and the magnitude. Magnitude bigger, confirm above level 1. Cannot be in between one. If it's in between, that means it's positive 70 or positive 30. So this is an implication because if I want to form the enthalpy, right, the enthalpy should be what? From here all the way up. Clear? Even before I calculate, let's say I use Hess's law, whatever, right? I know your A, B, and to C, D confirm is endothermic. So if I finish my calculation, right, my answer is negative. That will tell you it's wrong. That's why energy level diagram, if you ask me, is more superior than energy cycle. Because energy cycle, a candidate make a mistake, careless mistake, still cannot tell. Calculator calculate out already, right? Still cannot tell it's a careless mistake. Energy level diagram, I compare, I can tell. Oh, you get me? Okay, so now you see, I change the color, you can see a highlighter. I don't know whether your teacher teach it the same way. Okay, starting point here. Starting point here, right? A, I want to find this, right? So I follow the arrow. Must be from here to here. Hess's law. Yeah, you use a highlighter, just turn around the whole circle. Hess's law. Stage 1 to stage 2 to stage 3. So 1 to 2 to 3 must be the same as from 1 to 3. Okay, clockwise equals to anti-clockwise. Oh, Pasir Ris go to Boon Lay is the same as from Boon Lay. Pasir Ris go to Yishun, they come down to Boon Lay. Same. I'll use a highlighter. Mine is a pen. You all have a highlighter or any color, different color. You circle this. You turn the green round around, the green loop around. They can see better. Oh, ending point same. These are two arrowhead. Starting point, ending point same. Okay. Energy level diagram same thing. Okay. In exam, you must do a physical check. Can you see what happened? From here, go down, and then come up. Must be the same as from here, loop to here. Right? Hess's law. Yes, Richard?
How to know the starting one would be A plus B?
Oh, A plus B, then you see from the question, they say the reaction of A plus B to C plus D. So I started off with this part. Yeah. So step 1, I will draw this as my 1. But it's okay, even if you want to start off with EF to CD also can, but your diagram will be a bit different. Okay, so you can decide. But you will usually from a definition, you must start somewhere. Start from the one that is easier to recognize one. That means at the 0 level. Later you will see at 0 level. Usually this is as 0. 0 means at the baseline, relative energy is 0. When you see 0, that means elemental formula, calcium solid, chlorine is a gas at the elemental form. That means that nothing happened to them yet, is at 0 level. Usually we start from the 0 level one. Okay, good question. Jenny, okay? Cannot. Oh, I'm trying to unpack this because I understand why students struggle with energy level diagram, but I can tell you, you have no choice, because if the question asks for energy level diagram, you find energy cycle, you cannot you cannot get full marks. No? That's why you must train yourself to draw energy level diagram. You see 1, 2, 3, this kind of method. This one is a simple one. Later you see lattice energy, got a lot of them. 1, 2, 3, 4, 5, 6, 7, I think it was 6 of them. So you must know where is every energy level, no? Why is it above, why is it below that line? This is the training the mind part. Also later when we go through the lattice energy, it makes more sense to you. Okay, so now you see from here, right, can we solve using Hess's law, the two method? Okay, so for example, here energy cycle, can we say that negative enthalpy H equals to negative 100 plus positive 200, which is positive 100 kilojoules per mole. Okay, same thing, energy level diagram. So see, here, right, we do the same thing. Negative 100, I follow the number 2, this loop, this loop coming down, plus 200 must be the same as enthalpy H. So enthalpy H will be positive 100. Correct? Kilojoules per mole. Same answer. But you know why energy level diagram? I say, I told you all right. I know you all may have a phobia for energy level diagram, but it's very superior than energy cycle, because this answer is positive, right? You see, I look at my diagram, it's positive. Can you see that this is positive here in the energy cycle? Cannot see, no? At one glance cannot see. You see, energy cycle, I know most students like to draw energy cycle. Very easy, anyhow lump, not everyhow. You just position it. You don't have to follow energy level diagram, like how precise it is. That's why people enjoy drawing energy cycle. Most students use energy cycle to solve. I'm not stopping you to use energy cycle, but I want you to see the beauty behind energy level diagram. From the diagram and my answer, I check. I don't confirm correct. This is a simple one, okay? Later you draw lattice energy, same thing. You ask yourself, is your answer correct or not? You look at the magnitude. Can you see it's 100, right? This is 200. Your magnitude for this thing, the green star, cannot be bigger than 200. Then you check my answer, 100, correct? Shorter than 200. That is why energy level diagram tells us a lot of things. It tells us exactly whether we are on the correct direction. Hess's law, have you applied it correctly? Is your cycle drawn correctly? In the energy level diagram, everything is very clear. Okay, so don't be fearful of energy level diagram. Okay, you can ask your classmate, energy level diagram, so 麻烦 draw this thing. Don't want to use energy cycle. It's easier to draw, but then the thing is that there is value in energy level diagram. You train your mind to see energy level diagram. When you draw energy cycle, it's chicken feed. So you must take my advice. Every time you go to this chapter, draw energy level diagram. Force yourself to draw where possible. Okay, unless of course practice a few times, then you get the hang of it. Level 1, level 2, level 3, just like taking a leaf like that. How I know where is level 3? The question over here is always a question. Where is level 3? Blah, blah, blah. Okay, level 3, level 4, level 5. So that's how you can see how I know it's above, by observing the magnitude of this one and this one. Okay, how I decide to place level 3 on top. Okay, can you learn the same thing also, right? Energy level diagram in school, correct now. So again, like what I say, I'm not saying that my method is the best. Okay, but I'm trying to unpack for you, two of you, so that you all can see energy level diagram in the different light. Okay, can? Okay, now let's go on. Energetics, can we solve together exercise 2? Okay, can I give you some time to try? Right? Draw the energy cycle, energy cycle first. later then we practice energy level diagram for lattice energy. Remember, when you draw you are using Hess's law. When your values change cross the equal sign, make sure you change sign. I think you learned that in maths already, right? Oh, so I don't need to remind you. Okay, so this is a mathematical calculation. So if you make a mistake there also, the value is you cannot tell one. No, you cannot tell you got the wrong answer. Of course, here you can check lah. It's negative 112. Don't know whether correct or not. Okay, let's work together. Okay, so write down first, carbon, state symbol important because I need to see whether they go through any changes. Okay, so you can see here, right? Then after that, you are given carbon plus oxygen, give you carbon dioxide, right? So from here down, carbon dioxide. Okay, so this is negative 395 plus oxygen on the arrow. Oh, okay, then after that, your CO plus half oxygen give you CO2, right? So this is CO, CO2 here, plus half oxygen, right? Is it enough? Yeah, enough. CO2, so it's negative 283. This is enthalpy H. Okay, so by Hess's law, see, stage 1, stage 2, right? Curve clockwise, anti-clockwise, all the way down, here. Oh, you can see the green arrow. Okay, change back to red. Okay, so your enthalpy H, enthalpy plus negative 283 must give me negative 395. Enthalpy H is negative 112. Correct, you pick out a calculator and check for me. 112，对吗？Correct, very good. Oh, easy warm up example. Okay, right, same as your cycle. Your this half oxygen can you see from here? These two I put it on the arrow I put it on the arrow Okay, the mistake is that some student go and place it over here. Then they try to look for oxygen. Then here for plus another oxygen, you become what you call that? You have another oxygen on the left hand side here. It's okay because this is a side reactant. You can place it on the arrow Okay, but anyway you can check Okay, half of oxygen plus half oxygen over here also one oxygen So same You go through this round, the green arrow, can you see? Half oxygen plus half oxygen is still one oxygen so it's okay. Oh, that's a trick place on the arrow, place on the arrow. Oh, don't need to put down here and then you make the whole thing very cumbersome. Okay, can Okay, next one, question exercise 3, you'll try. Practice one energy cycle is like that okay? You don't practice, you're rusty, very difficult to do Okay, so we copy down the equation SnO2 solid, 2CO gas, and you are given Sn solid and 2CO2 gas, enthalpy H. Correct? Okay, so what are we given? Sn to SO2, right? Sn here. Carbon. Then what else? Carbon to carbon dioxide, right? Here, carbon formation of 2 carbon dioxide from here to here is negative 394. This one is, where? We'll start for SNO2 first, minus 581. This one 2 moles, so 2 times negative 111, correct? Still got 2 here, times 2. Oh, so you must know your definition well, then you can do the way I do it. If you're not sure for definition, then you have to write the equation out. Write the equation out here. You know what I'm talking about? If you know the definition, actually the question don't need you to write the definition. But if let's say you are not familiar with the definition, what is enthalpy change of formation? It's 1 mole of this, right? So I see it's Sn here, confirm is on Sn, then plus oxygen, right? Oxygen on the arrow if you want to. Then your oxygen here on the arrow. Then your this one carbon, oxygen. Oxygen, how many oxygen? Here you need 2 oxygen, right? Carbon, you need 2 oxygen to form 2 moles. Okay, so I check. Let's take a look from the enthalpy change. Here, from here to here, right? So you can swing one big lump, and you can also swing from here to here. Hess's law. You see the one I do in green is what I actually do as a student. To remind myself, I follow the arrow in which direction. Make sure they are flowing. I'm using very layman term of Hess's law. Make sure it's flowing. Make sure your arrow head is flowing the same direction. You see all the red arrow go up and then go across. Then from here is one direction to this one. So I draw it this way to remind myself. Clockwise, anti-clockwise. So clockwise equal to anti-clockwise. This is what I'm trying to do. Training, you always do this one. Okay. Exam, of course, you can see the green arrow without doing this. You just carry on. Okay, don't need to draw the green arrow. But practice, you should do that. Okay. So let's calculate all of them. Let's change back to my red pen. Can you calculate? Minus 581 plus 2 times minus 111 plus enthalpy equal to 2 times negative 394. Enthalpy H equal solve. I think it's positive 15. 对吗？ Correct, Rachel? Okay. Is it correct? Your calculator check for me. Check. Make sure it's correct. Make sure it's correct. Positive 15. Correct? Wrong?
Yeah, correct.
Correct. This. I also don't know. Mr. Lai says this answer. I don't know whether he go and calculate. I just follow what he said. Then his answer is here. Then I just calculate. I just work out on the spot. Correct? Okay. Good. Everybody happy? Then you cannot. Can? Okay, good, no problem. Okay, let's go on. Okay, exercise 4, enthalpy change of the formation of propanol. Propanol is alcohol, third member. So it's this one, C3H7OH. Okay, so 316. Okay, so you can try. You all try first to form the equation, or maybe I help you all with the enthalpy change of formation of propanol first. So start from here. See how I do. Right here first. Okay, I know it's not very like that. I start from here first because I remember definition of formation of propanol is 1 mole. I control 1 here. Then I write the rest of carbon, solid, and then you have hydrogen, and then you have oxygen, right? So gas and gas are in the elemental form. Then I balance the oxygen. Here I need half. Correct? Then you have 4 hydrogen here, right? So this one is, 8 hydrogen on the right. So this is a 4. You must get this first, no? This is what they are trying to ask you to find, enthalpy H of formation. This is an enthalpy H of formation from the definition. 1 mole of propanol. Okay, then the rest will come in already. Okay, swing in the rest of. What do I have? So you have combustion. Combustion means you burn this propanol completely, right? So you start with combustion first. This fella, when you burn completely, is carbon dioxide plus water. Knowledge you must remember. Combustion of propanol, organic compound, will give you carbon dioxide plus water. Then I will need to balance these two, right? Because I need to check the equation first, So there is a 3 here, right? So I think I need a 3 law. Water, I have 8 here, right? There's only 2 water here. I need a 4 law. So everything is taking shape. Then I can slowly plug in the rest. They say the enthalpy change of combustion of carbon is 394. So from here to here, sure with one arrow. Right, so it's 394. Okay, 394. Then you have minus 394. Minus 394. This one, hydrogen to water is 286. Here got 4. So it's 4 times negative 286. This one, I have combustion. I have a minus 2010. Then you double check. Make sure everything is in. Is it 3 here? I think it's a 3. Wait, let me check the paper. Is there a 3 here? I think it's a 3. 3 moles, right? Yeah, 3 here. Okay, because there's a C3, I never write in C3 here. Okay. Is that one along the way patch? Patch. Okay. Everything balanced. 3 here, 3 here, 3 here. Here is 4. Okay, then we solve. Hess's law, clockwise equals to anti-clockwise. From here, swing up, come down, follow the arrow. Here. From here, come down to here. The 2 arrow head meet. Yes. Correct? Then I can solve it here. Enthalpy H formation plus negative 2010 must be the same as 3 times negative 394 plus 4 times negative 286. Can we solve? Is it this one? Right, calculators. So you can form the cycle first. Don't rush. Make sure you all can form the cycle first. Any question about the cycle, let me know. Anything missing? Anything odd? Negative 316 kilojoules per mole. Yes, Rachel?
Why is it that H2 must the energy 286 plus times 4? Why not times 2?
Times 2, but you have 4 moles here. Enthalpy change of combustion. For is 1 mole of hydrogen burn complete oxygen, but you have 4 here. So you need a 4. And there's a 4 here also. You see the 3 of them in circle, 4. So you must remember, first step, you must not get it wrong, which is this one. Can you see the first step? What is enthalpy change of formation of propanol? I must build the first equation first. So I can see a 4 appearing here, a 3 appearing here. I roughly know that this 3 and this 4 is reflected here already. At the back of my mind before I start drawing the whole cycle. That's why the first step is very important. Get the first step out first. the enthalpy change of formation or proper no. Don't make it, don't make a mistake there, then the rest will fall in place. The rest will just sure the cycle can come out. Oh. Okay, so you can. All right. Practice. You have more questions in the tutorial, I think, for practicing. Okay, for you to practice this afternoon. Next week we'll have more question to do because enthalpy change of reaction, this kind of energy cycle, you need practice and of course the what do you call that? The definition very important. You can see that when I craft the equation, I don't even write down the equation out. I know a lot of teachers will write down the equation by the side. Yeah, by all means do that if you are not familiar with the equation. But imagine if this is a MCQ question, you don't have time, you don't have time to write down everything, then go and do the MCQ like the structured question. You will be unable, you may not be able to complete the paper on time. Also, you must know how to churn out the whole cycle without having to write all the equations out for all these enthalpies. You must train your mind to see them. Train your mind to see them, then you'll be very fast. Okay. So you cannot. Any problem? Come, don't be shy. Can your calculator out already? Is it 316? I don't know because this is a value. They give an answer like that. Sekali the answer is wrong. Correct? 316. Okay, done. Can we move on? So you okay? Okay, very good. Next question. Okay, enthalpy change of reaction involving bond calculation involving bond energy. Okay, this formula very important. Okay, I know some teacher teach student to invert sign and then insert inside enthalpy change of reaction. I don't do that. I follow this one. I follow this for both my O-level student and my A-level student. Let the negative sign take care of it. Okay, so bond energy. Bond breaking energy minus bond forming energy will give you enthalpy change of reaction. Okay, in fact, I will summarize this as the following reaction here. Okay, I write down here. Okay, so this equation, right, is like that one. Enthalpy change is your bond breaking, bond energy, all the bond energy or bond breaking, BB, minus bond energy or bond forming of the reactants for bond breaking and products for bond forming. It makes sense. Energy taken in for bond breaking minus the energy given out from bond forming will tell you where the loop stop. Remember your energy diagram? Your energy go up and then come down, right? So you take the bond energy of your reactant, initial minus final, that will tell you whether it's positive or negative. Positive is endothermic. Negative is exothermic. So you just need to do that. Take the bond energy sub in and then you solve it. Or don't go and flip the sign. Okay, so this is what we will do for exercise 5. Okay, so in exercise 5, you can see from here, you number 1, we will use the formula. So bond breaking, bond energy for bond breaking of reactants. Can you see? You are breaking, you must observe. Okay, some students go and break everything, Then they say got 6, 1, 2, 3, 4, 5, 6. They say got 6 CH bond. But you observe very carefully, they only break 1 CH bond plus 1 Cl bond. That's all they are breaking. No more already. Okay, what about number 2? What about the bond energy for the bond breaking? Bond energy for bond forming, right? Bond forming of products. What are the bonds that are being formed? Over here, you have 1 CCl bond, correct? That's being formed. Can you see that? CCl bond that's being formed in C2H5Cl plus 1 HCl bond. That's all. You observe carefully the reactants and the product. All right. Okay, now you take your data booklet. I think you should be able to find these 2 values, add them up together, you get your X. These 2 values, you add your Y. So your enthalpy is just X minus Y. Don't forget the sign. Okay, you get the answer. Yeah, let me see. I don't have my data booklet. Can you find it? Can you find the CL bond? Oh yeah, I have. You have this, right? You cannot see the data booklet. The purple one. You all have this piece of paper. Data booklet. That time I think we all issue to all of you. Can you find the bond length? CL. Okay, we find anything, we just write down 244. This one on top is 244. Can you find? HCl is 431. This one is 431. Then your CH bond, where is it? CH bond is 410. And then your CCl bond is 340. Okay, mula. Alright, calculator. 410 plus 244. Then 340 plus 431. 771 minus 771 minus 117. Correct? Yes. Yeah. Correct. Correct. Okay. Correct. So remember, let the negative sign take care of the conversion. Just take and then plug inside the formula, finish. Don't do any cosmetic. Change sign, flip here, flip there, in the end, lost inside. Okay, question? Can you okay not? Can you okay? You understand this formula, how I use it, and where to find all this value inside the paper, the piece of paper that we give you. You also have a data booklet. I think your teacher have issued you all a data booklet already. You all know, right? The one with a lot of pages. We summarize all the key one for you inside that piece of paper. Okay? Rachel, okay? Can solve? Any part you want to ask?
Yes. Why never include the C2H5Cl?
Because it's not broken. Remember, your C2H6 is your ethane. Ethane, when you in this reaction, right, they only break one CH bond. If you remember this mechanism, you learned that at O level, free radical substitution. So you only break one bond. Yeah. But if you, let's say you want to do everything, also can, because your left hand side and the right hand side, they will cut away each other. But what I'm trying to tell you is that it's only breaking one bond. If you remember your your substitution reaction at O level, actually it's called free radical substitution, the full name. I think at O level, they all teach you, they tell you it's substitution reaction, but the full name is free radical substitution. Okay, so at A level, when you come to alkane, you will know that. So that is where one bond is being broken only. Okay, okay, next week then I will go into bond-Haber cycle. Okay, so ionic compound. But at the same time, you all can start your tutorial question already. The first set, I think you all have some question inside. You all can try out all the energy cycle. So next week, when I complete the bond-Haber cycle for ionic compound, we can jump straight into all the tutorial question first. Then we come back to do entropy. Okay, entropy is also downplayed inside your syllabus because it's covered in physics, part of it. Okay, so we are not going to very difficult calculation. Okay, we just need you all to understand what we meant by Gibbs free energy and then entropy. I think by now you all should know what they meant. Okay, so I will highlight to you again on that part. But this chapter, like what I say, the more practice you have, the better you become. Okay, and always remember, take my advice. Energy level diagram is not fearful, and if you follow the way I teach you, remember I tell you level 1, level 2, level 3, like climbing stairs like that. but in your mind, you must be able to project the value and the magnitude. Then you know whether level 3 is on top of level 1 or level 3 is in between level 1, 2 or even below level 2. All this is training your mind by looking at the magnitude to draw. The best way to do it is to draw your Born-Haber cycle, because your Born-Haber cycle, right, for your ionic compound involve the calculation of lattice energy. So you practice that, you have a lot of opportunity, right, to learn how to construct energy level diagram. Okay, so if you ask me in exam, if they ask you for energy level diagram, you have no choice, or you need to do it. Okay, you cannot say I draw energy cycle, try to escape. Cannot. You won't be given full credit. Okay, it's not the magnitude of the value only. Okay, can okay, so you no problem there. I'll see you next weekend. All right, get ready for next session. So same thing, next week you all can come in earlier, then we start earlier already. Or 8:50 also can, 8:30 also can. Never mind, you all haven't wake up yet, right? Okay, so if you usually about 8:50 I think fair enough not too early. Otherwise you all too not enough sleep. Can okay. So practice more. See you all next week. Hey, bye bye. Yeah.